The resounding thunder of 4 memory engines reverberated across the expanse of the runway as the Nakajima G5N Shinszan, Japan's inaugural heavy bomber, embarked on its arduous journey down 40,200 feet of concrete. Weighing an imposing 44,313 pounds when empty, this gargantuan airframe was a full 8,000 pounds heavier than its American counterpart, the B-17 Flying Fortress. The test pilot grappled with the aircraft's ponderous and unresponsive controls as the massive machine eventually clawed its way into the sky, achieving a meager climb rate of barely 500 feet per minute, a mere half of what an American bomber could accomplish. Below, within the hangars, Chief Engineer Kenichi Matsumura observed the struggling ascent through his binoculars. His meticulously kept notebook, already filled with prescient calculations that had, in theory, foretold this very moment of operational difficulty. Japan had, with considerable anticipation, acquired the sole Douglas DC-4E prototype in 1939 for a sum of $275,000, firmly convinced they had secured the coveted schema for America's undeniable aviation supremacy. What followed was a painstaking 2-year endeavor of reverse engineering, involving hundreds of highly skilled workers and the allocation of the finest materials Japan could muster, all dedicated to constructing their own version of what they perceived as American excellence. Yet, as the Shinszan faded into the morning haze, visibly struggling to maintain its altitude, a profound and devastating truth began to crystallize. Merely copying American technology was proving insufficient. A deeper understanding of the underlying design philosophy, the why behind America's engineering choices, was absolutely paramount. Stay with us and watch the end of the video. We will be grateful for your like and subscription. Write a comment about where you are from and what you think about the video topic. The early morning sun cast long, dramatic shadows across Oda Airfield as Kenichi Matsumura meticulously adjusted his stopwatch, poised to witness what Imperial Japanese Navy headquarters fervently believed would be their definitive answer to American strategic bombing capabilities. The date was April 8, 1941, and the colossal Nakajima G5N Shinszan sat at the terminus of the runway like a metallic mountain range, its 4 mammary engines already warming with deep, throaty rumbles that sent resonant tremors through the very concrete beneath Matsumura's feet. Matsumura himself had dedicated a grueling 18 months to overseeing every single rivet and wire of this ambitious aircraft, driven by a singular, pervasive obsession that had consumed Japan's aviation industry since the initial stages of Pearl Harbor planning began. The Americans possessed a critical capability that Japan desperately needed: the inherent ability to strike industrial targets located as far as 2,000 miles from their operational bases. The B-17 Flying Fortress, in particular, epitomized everything Japan currently lacked. Engines renowned for their unwavering reliability, formidable defensive firepower, and, most critically, the operational range required to carry the war directly to enemy soil. Standing vigilantly beside the runway, clipboard firmly in hand, Matsumura watched Major Katsuaki Kira complete his meticulous pre-flight checklist within the Shinzan's cockpit. The bomber itself stretched an imposing 138 feet from its nose to its tail, its silver aluminum skin gleaming brilliantly in the nascent light of dawn. On paper, the aircraft's specifications appeared unequivocally formidable: a bomb capacity of 4,000 kilograms, an impressive range of 3,500 miles, and defensive armament strategically positioned to theoretically shred any intercepting fighters. The Navy's procurement officers, in their enthusiastic projections, had already hailed it as Japan's war winner, the decisive instrument that would ultimately bring American industry to its knees. However, Matsumura's own engineering notebooks presented a contrasting narrative, filled with disquieting figures and calculations that had been troubling him for several weeks. The empty weight was recorded at 313 pounds. Intelligence reports gleaned from captured B-17G documents, however, indicated that American bombers weighed a mere 135 pounds without fuel or ordnance, a stark divergence of 8,000 pounds for essentially the same mission profile. This significant discrepancy violated every fundamental principle of aircraft design that Matsumura had assiduously learned and refined over his 2-decade career. The memory engines, with a sound akin to sustained thunder, finally achieved full power, each of the 4 radial units producing a robust 9,870 horsepower, culminating in a collective might of 7,180 total horsepower, designed to lift an astonishing 62,060 pounds at maximum takeoff weight. Matsumura, with the instinct born of years of experience, automatically computed the arithmetic. 120 horsepower per 1,000 pounds. In comparison, the B-17G achieved a more efficient 133 horsepower per 1,000 pounds with its Wright cyclones, and those American engines had demonstrably proven their endurance and reliability through hundreds of demanding combat missions over the European theater. Major Kira, with a final decisive movement, released the brakes, and the Shinszan began its takeoff roll, commencing slowly at first, then gradually gathering a momentum that seemed to stretch into an interminable duration. 1,000 feet down the runway, then 2,000 feet, then 3,000 feet. Matsumura's stopwatch precisely showed the bomber consuming a staggering 4,200 feet of concrete before its nose wheel finally lifted clear of the ground. A B-17, under comparable conditions, typically required only 2,200 feet, half the distance, for an aircraft that offered twice the proven reliability. The Shinszan ascended at what could only be described as a grudging pace, reluctantly gaining altitude at barely 500 feet per minute, while Major Kira engaged in an arduous struggle with controls that responded as if submerged in a viscous fluid. Through his binoculars, Matsumura could clearly discern the pilot's helmet moving constantly, a testament to the continuous perceptible adjustments required to compensate for the bomber's inherent tendency to wallow sluggishly through the air rather than fly with a purposeful trajectory. American B-17s, in stark contrast, climbed at a brisk 900 feet per minute, their crews frequently reporting that the aircraft felt eager and responsive, keen to reach its designated bombing altitude. As the Shinszan slowly faded from view into the morning haze, visibly struggling to maintain its hard-won altitude, Matsumura finally grasped the profound magnitude of Japan's erroneous assumption. 2 years prior, in 1939, Japanese negotiators had triumphantly purchased the sole Douglas DC-4E prototype for $275,000, genuinely believing they had acquired the ultimate blueprint for American aviation supremacy. The massive 4-engine airliner had initially seemed perfectly suited for adaptation to military use. A sweeping 138-foot wingspan, robust all-metal construction, a practical tricycle landing gear, and 4 powerful engines arranged in the identical configuration as the formidable B-17. However, the critical detail they had overlooked was that the DC-4E had been decisively rejected by American Airlines, deemed fundamentally too complex and excessively expensive for viable commercial operations. United Airlines, Eastern Airlines, and American Airlines had all meticulously scrutinized the prototype and, in a unanimous decision, concluded that it was excessively robust, over-engineered, and inherently impractical for profitable service. The very aircraft that Japan had mistakenly thought represented the pinnacle of American technological prowess was, in reality, American industry's most expensive and commercially unviable misstep. Matsumura's dedicated team had painstakingly dissected and reverse-engineered every single component of the DC-4E with meticulous precision, operating under the misguided premise that American design philosophy inherently prioritized brute strength above all considerations of efficiency. Consequently, they had reinforced structural elements that were already excessively robust, added superfluous defensive positions that merely increased the aircraft's weight without any tangible improvement in capability, and installed engines that, while producing adequate power, critically lacked the unwavering reliability essential for sustained combat operations. The mammary radials, lamentably, failed every 50 flight hours, necessitating complete overhauls that consumed irreplaceable materials and highly skilled labor. In stark contrast, Wright Cyclones, in American service, routinely operated for a remarkable 400 hours between major maintenance interventions. The irony was devastating in its implications. Japan had squandered 2 years and millions of yen meticulously copying an aircraft that Americans had long since abandoned as commercially unviable, only to then make it even heavier and more complex in their earnest, yet ultimately flawed, endeavor of military adaptation. The complex tapestry of military adaptation often reveals that sheer technical brilliance alone cannot guarantee strategic success. Every meticulous calculation meticulously entered into Kenichi Matsumura's engineering notebooks unequivocally corroborated the stark reality unveiled during that morning's critical flight test. The Shinszan, while an undeniably magnificent testament to precision engineering, was fundamentally flawed, a dazzling example of masterful craftsmanship misapplied to an unsuitable foundational concept. It was a testament to design perfection, yet utterly inadequate for its intended strategic role. A faint crackle of radio static punctuated the air within the control tower. As Major Kira, the test pilot, relayed his position report, precisely 20 minutes into the ambitious flight. While comprehensive service ceiling evaluations were slated for a later stage, the preliminary indications painted a grim picture, suggesting that the Shinszan would encounter severe difficulties in ascending beyond an altitude of 24,000 feet under authentic combat conditions. This was a critical vulnerability, especially when contrasted with the American B-17 flying fortresses, which habitually cruised at altitudes ranging between 25,000 and 30,000 feet. These formidable bombers leveraged their superior operational height as their primary defensive bulwark against any intercepting fighter aircraft. Consequently, the American heavy bombers operated comfortably within an atmospheric band that Japanese fighters could barely aspire to reach, effectively transforming the vast expanse of the sky itself into an impregnable defensive territory. As Matsumura retraced his steps, his gait heavy with the weight of revelation, back towards the expansive engineering hangar, his brilliant mind was already meticulously dissecting the profound implications stemming from the morning's undeniable failure. Japan, he acutely understood, harbored a desperate, existential need for strategic bombers. Yet the prevailing approach of directly replicating American technology had unequivocally proven to be woefully insufficient. The substantial investment in acquiring the DC-4E had been predicated upon a misguided assumption that merely possessing enemy hardware would automatically confer enemy capability. However, Matsumura now recognized with chilling clarity that true capability was not inherent within the static lines of a blueprint, but rather deeply embedded within the intricate industrial philosophy that had conceived and brought those blueprints to life. We invite you to stay with us and watch the remainder of this insightful video. Your support, in the form of a like and a subscription, would be immensely appreciated. Please also consider leaving a comment below, sharing where you are from and your thoughts on this compelling topic. American aircraft designers, it became evident, transcended the mere construction of flying machines. They meticulously engineered aerial platforms that could be mass-produced by the thousands, effortlessly maintained by mechanics possessing only rudimentary training, and reliably operated under the harrowing crucible of combat by relatively inexperienced 20-year-old crew members. In stark contrast, Japanese engineers, with their unwavering dedication to perfection, crafted what could only be described as mechanical masterpieces, intricate aircraft demanding unceasing vigilance and skilled attention from master craftsmen, machines that, while technically sophisticated, were inherently operationally fragile. It was a bitter truth, but the Shinszan, Matsumura now realized with certainty, would never progress beyond the prototype stage to enter full-scale production. Even as Major Kira skillfully brought his test flight to a conclusion and initiated the intricate procedures for landing, Matsumura harbored no illusions. He knew, with a sinking certainty, that Japan's initial ambitious endeavor to emulate American strategic bombing capability had catastrophically failed even before it had truly begun to take wing. Yet, amidst the profound disappointment, a nascent realization flickered within him. Perhaps such a monumental failure held within it invaluable lessons, profound insights that the elusive hand of success could never adequately provide. Spring, a season typically associated with renewal and burgeoning hope, arrived at Nakajima's Kisumi facility, imbued with a palpable, almost desperate urgency. This fervent atmosphere was directly fueled by the Imperial Japanese Navy Headquarters' unshakable, almost dogmatic conviction that Japan's nascent strategic bomber program could yet be the decisive instrument for achieving ultimate victory. Despite the Shinzan's undeniably disappointing performance metrics, Admiral Isoroku Yamamoto's influential staff had promulgated new directives that verged on the utterly impossible: to conceive and develop a heavy bomber capable of striking the American mainland within an impossibly tight 18-month time frame, lest Japan's critical window of strategic opportunity irrevocably close forever. Consequently, Kenichi Matsumura found himself ensnared in a relentless regimen of 16-hour workdays, his dedicated engineering team dramatically augmented to encompass over 200 highly specialized experts, all of whom had been forcibly diverted from every other significant aircraft development project across Japan. The Navy's steadfast faith in the Shinzan remained curiously impervious to the accumulating evidence of its shortcomings, a conviction primarily rooted in the aircraft's impressive specifications as they appeared on official procurement documents. A substantial 4,000 kilometer bomb capacity, an extensive 3,500 miles of operational range, and a formidable defensive armament comprising 4 20mm cannons, complemented by 12 7. 7mm machine guns. On paper, the aircraft presented a compelling profile seemingly capable of inflicting devastating damage upon American industrial targets stretching from the remote Aleutian Islands all the way to the sun-drenched coast of California. However, Matsumura's meticulously gathered flight test data narrated a profoundly different and increasingly disquieting narrative, one that grew more troubling with the completion of each successive mission. The Shinszan's maximum speed, a mere 261 km/h, rendered it inherently vulnerable to virtually any contemporary fighter aircraft encountered in combat. Concurrently, its operational service ceiling of just 24,450 feet left it precariously exposed to enemy interceptors, which could launch devastating attacks from above with absolute impunity. Captured intelligence reports painted a stark picture of American P-38 Lightnings, aircraft capable of ascending to an astounding 39,000 feet and achieving speeds exceeding 400 mph during their terrifying diving attacks, highlighting the vast disparity in performance. Even more devastating than the aircraft's performance shortcomings were the pervasive and systemic engine reliability problems. The mammary radial engines, the very heart of the Shinszan, demanded complete overhauls after a mere 50 flight hours, a requirement that voraciously consumed precious aluminum alloy, a material Japan could scarcely afford to allocate in such quantities. Each individual engine incorporated components machined to incredibly fine tolerances, necessitating the expertise of Japan's most skilled workers, artisans who were, paradoxically, desperately needed for the burgeoning production of Zero fighters as the conflict inexorably expanded across the vast Pacific theater. To exacerbate these issues, the mammary power plants generated severe and persistent vibrations that alarmingly loosened crucial instruments, catastrophically cracked fuel lines, and rapidly fatigued the very structures of the airframe, posing a constant threat to operational safety. In stark contrast, the robust Wright Cyclones, retrieved from captured B-17s, displayed wear patterns entirely consistent with an impressive 400 hours of operation between major maintenance interventions, a testament to their superior endurance. Quelque part, the underlying American engine design philosophy deliberately prioritized unwavering reliability over the pursuit of peak performance, willingly accepting a marginally reduced power output in exchange for a dramatically enhanced operational availability. This pragmatic approach meant that a B-17 squadron could sustain a high level of combat readiness for months on end, a stark contrast to the Shinszan bombers, which, it was clear, would inevitably spend a disproportionate amount of their operational lives languishing in maintenance hangars rather than executing vital combat missions. Matsumura's dedicated team had commenced conducting exhaustive forensic examinations of Wright R-1820 engines salvaged from B-17s that had been shot down over the Philippines. The profound disparities in manufacturing philosophy between the two nations were immediately and glaringly apparent. American cylinder designs incorporated simpler cooling fins, meticulously engineered for efficient mass production utilizing automated machinery. Conversely, Japanese engines showcased intricate cooling patterns that imperatively demanded individual hand finishing by revered master craftsmen, a process both time-consuming and resource-intensive. Similarly, American connecting rods were robustly forged from standardized steel alloys, promoting consistency and ease of supply, whereas Japanese rods often utilized exotic metals that, while theoretically enhancing performance, simultaneously created debilitating supply chain bottlenecks. the fundamental and pervasive problem extended far beyond the realm of individual components, encompassing the entirety of the industrial approach. American aircraft manufacturers meticulously designed their aircraft with mass production as a core consideration from the initial drawing board stage, conceiving machines that could be efficiently assembled by a workforce possessing minimal training, utilizing standardized tools and meticulously defined procedures. Japanese designers, however, meticulously optimized for the pinnacle of performance and the artistry of craftsmanship, resulting in aircraft that demanded the constant involvement of highly skilled artisans at every single stage of the production process. The inevitable outcome of this divergent philosophy was the creation of bombers that, while performing magnificently when brand new, rapidly degraded under the brutal realities of combat conditions, necessitating unremitting attention from specialized personnel, who were becoming increasingly scarce and difficult to replace. By the summer of 1941, the Shinszan program had already consumed an astounding quantity of resources, an expenditure equivalent to the construction of approximately 300 Zero fighters. Yet, despite this colossal investment, it had yielded a paltry sum of merely 6 prototype bombers, production rates that might have seemed marginally adequate during the serene projections of peacetime planning, proved catastrophically insufficient as the war explosively expanded far beyond anyone's initial conservative projections. In stark contrast, American factories were already achieving impressive delivery rates of B-17s, turning out 20 aircraft per month from single production lines, with multiple additional facilities strategically planned for activation as the escalating military orders continued to surge. The escalating demands from the military led to a significant increase in orders, yet concurrently exacerbated a persistent challenge: the weight problem that had plagued the Shinszan aircraft since its maiden flight. This issue grew progressively worse with the integration of each additional piece of equipment. For instance, the crucial armor plating, designed to protect vital systems, contributed an extra 200 pounds to the bomber's total mass. Furthermore, enhancements to the aircraft's defensive armament added another substantial 800 pounds. The indispensable self-sealing fuel tanks, absolutely critical for ensuring the bomber's survivability deep within hostile airspace, alone inflated the empty weight by a considerable 1,500 pounds. This series of modifications, each intended to bolster the Shinszan's combat effectiveness, paradoxically diminished its already precarious performance characteristics. This created a perilous, self-defeating cycle where improvements meant to enhance survival inadvertently rendered the bomber too sluggish and unwieldy to effectively evade the very threats against which it was being fortified. Kenichi Matsumura's meticulous calculations painted a grim picture, revealing that a Shinszan fully laden with its maximum complement of fuel and ordnance would grapple severely just to maintain altitude if even a single engine were to fail during a mission. The flight characteristics under twin-engine power bordered on outright dangerous, while the aircraft's performance with only one engine operational made any attempt at a successful landing questionable at best, if not entirely improbable. This stark reality stood in stark contrast to intelligence reports concerning American B-17 crews, who were routinely observed bringing heavily damaged bombers back to base on merely 2 engines, and on occasion even managing to return safely after losing half of their power plants to intense enemy action. Stay with us and watch the end of the video. We will be grateful for your like and subscription. Please leave a comment below about where you are from and what you think about the video topic. The crippling scarcity of aluminum, an issue that began to severely impact all Japanese aircraft production in the latter part of 1941, struck the Shinszan program with particular and devastating severity. Each individual Shinszan bomber necessitated an enormous 8 tons of aluminum alloy for its construction, a figure considerably higher than the 5 tons required for a nimble Zero fighter, or the modest 3 tons for a more typical Army bomber. Japan's entire aluminum production capacity could theoretically sustain the manufacture of just 12 Shinszan bombers per month. But this was an optimistic scenario that assumed no other aircraft were being produced simultaneously. The harsh realities of wartime priorities meant that the ambitious heavy bomber program was in direct fierce competition with fighter aircraft initiatives, which were desperately and immediately needed for the critical defense of the homeland. American aluminum production, according to the most recent intelligence estimates, had by 1943 soared to exceed an astonishing 900,000 tons annually. In stark contrast, Japanese production peaked at a mere 142,000 tons in 1944, creating an insurmountable resource gap that fundamentally precluded any possibility of large-scale bomber production, irrespective of how efficient the aircraft's design might be. Even if Matsumura's dedicated team had somehow engineered an absolutely perfect aircraft, Japan simply lacked the fundamental industrial capacity and raw material abundance to construct it in numbers significant enough to exert any meaningful strategic impact. The profound psychological toll on his engineering team became increasingly palpable and evident as successive test flights continued to uncover deep-seated fundamental problems. Workers who had dedicated months to meticulously perfecting individual components watched with a sense of helpless futility as their exquisite craftsmanship was repeatedly negated by pervasive systemic design flaws that defied correction through mere incremental improvements. The Shinszan, it became clear, demanded a complete and radical redesign from its very foundational principles. A comprehensive overhaul that Navy procurement schedules, unfortunately, allowed no time for. Starting over was simply not an option, given the pressing wartime demands. By the advent of autumn, Matsumura had arrived at a profound and unsettling conclusion, one he dared not articulate openly in official meetings. He recognized that Japan was fundamentally constructing the wrong aircraft, employing inappropriate methods, for an entirely misjudged strategic situation. The Shinszan, in essence, embodied everything that Japanese engineering traditionally excelled at: precision manufacturing, an obsessive attention to minute detail, and the meticulous optimization of individual components, yet it was being applied to a mission that required precisely what Japanese industry struggled with: robust mass production, simplified maintenance protocols, and a design philosophy centered on inherent reliability rather than absolute perfection. The captured B-17s, now sitting silently in Japanese hangars, served as daily stark reminders of a profoundly different and evidently more effective approach to aviation engineering. However, merely understanding the American design philosophy and successfully implementing it were two entirely distinct and immensely challenging endeavors. While Japan possessed the technical acumen to design and build superior bombers, it tragically lacked the indispensable industrial infrastructure required to produce enough of them to truly matter on a strategic scale. The captured B-17E arrived at Nakajima's sprawling facility on a flatbed truck convoy in March of 1942, its aluminum skin still bearing the visible scorch marks from the fierce fighter attack that had ultimately forced it down in the Philippines. Kenichi Matsumura stood stoically beside the cavernous hangar doors, as skilled workers meticulously maneuvered the remarkably intact bomber inside, a complex mixture of professional anticipation and an underlying sense of dread swirling within him. For 18 arduous months, his dedicated team had been engaged in the painstaking process of reverse engineering the DC-4E prototype, operating under the assumption that they had grasped the core tenets of American design philosophy. Now at last they would have the opportunity to scrutinize the authentic article. The legendary flying fortress, upon initial inspection, appeared deceptively smaller than Matsumura and his team had anticipated. Its wingspan of 103 feet seemed almost delicate when juxtaposed with the Shinszan's truly massive 138-foot spread. Yet, as Matsumura's elite inspection team commenced their rigorous, systematic examination, the profound and fundamental differences between the two aircraft became strikingly apparent, challenging every preconceived assumption they held about American engineering prowess. Notably, the B-17's empty weight of 36,135 pounds was a staggering 8,000 pounds lighter than the Shinszan, despite the American bomber carrying a remarkably similar defensive armament package and comparable fuel capacity. Matsumura personally oversaw the intricate engine removal process, intently observing as expert technicians painstakingly extracted the powerful Wright R-1820 Cyclone radials that had so reliably propelled this particular fortress across thousands of miles of the vast Pacific Ocean. Each of these formidable engines weighed 1,250 pounds and was capable of generating an impressive 1,200 horsepower at takeoff settings. In contrast, the Shinszan's memory engines, while more powerful at 1,870 horsepower, also weighed a heavier 2,100 pounds each. This seemingly impressive power-to-weight ratio of the memory engines only appeared superior until directly compared with the stringent and remarkably efficient American engineering standards. A thorough examination of the Wright Cyclone's internal components revealed wear patterns that eloquently narrated a remarkable tale of exceptional operational reliability and endurance. The cylinder walls, for instance, displayed an even and consistent scoring, indicative of hundreds of flight hours under demanding conditions, while the connecting rod bearings exhibited only minimal degradation, despite clear evidence of significant combat stress. Perhaps most astonishing was the sheer simplicity of the cooling system design. Straightforward, straight fins, precisely machined with automated equipment. A stark departure from the intricate, complex, curved patterns that Japanese engineers had previously assumed were absolutely necessary for adequate heat dissipation. The comprehensive teardown of the American engines ultimately unveiled a manufacturing philosophy that directly contradicted nearly everything Matsumura had been rigorously taught about the principles of precision engineering. The tolerances, surprisingly, were considerably looser than what Japanese standards would typically deem acceptable. Yet, paradoxically, these engines operated with far greater reliability than the memory radials, which were meticulously constructed to much tighter and more demanding specifications. It became evident that American designers had consciously optimized for consistent, dependable performance, rather than chasing peak, momentary output, willingly accepting a slightly reduced efficiency in exchange for dramatically improved maintainability and overall operational robustness. The structural distinctions in the airframe proved profoundly illuminating for the observers. The wings of the B-17, for instance, incorporated spars crafted from aluminum extrusions, components that lent themselves readily to large-scale production through the efficiency of rolling mills. Reinforcement in these structures was judiciously concentrated at points of high stress, rather than being uniformly distributed across the entire framework, a design choice optimizing both material use and manufacturing ease. In stark contrast, Japanese engineers had conceived the Shinszan's wings using intricate forgings, each demanding individual machining. While these parts were theoretically superior in their inherent strength and precision, their complex fabrication rendered them practically impossible to produce in the vast quantities required for sustained warfare. Matsumura dedicated numerous hours to an exhaustive examination of the B-17's electrical systems, expressing considerable admiration for the profound standardization that permitted the replacement of any component with minimal specialized training. The wiring harnesses, meticulously designed, featured color-coded insulation and universally standardized connectors, effectively eliminating any ambiguity or guesswork during critical field maintenance operations. Furthermore, control cables were intelligently routed through easily accessible channels, punctuated by inspection plates at regular intervals, a thoughtful design element that empowered mechanics to swiftly pinpoint and rectify problems. Conversely, the Shinszan's electrical architecture mandated a deep, specialized understanding for servicing, characterized by bespoke connectors and concealed routing that transformed troubleshooting into an arduous and exceptionally time-consuming ordeal. We invite you to stay with us and watch the end of this narrative. We would be immensely grateful for your like and subscription. Please also consider sharing where you are from and what your thoughts are on the crucial topic of design philosophy in wartime manufacturing. The configuration of the defensive armament installations unveiled yet another foundational divergence in engineering philosophy. B-17 gun positions were ingeniously designed for swift installation and removal, featuring standardized mounts capable of accommodating various weapon types as dynamic mission requirements evolved. The ammunition feed mechanisms relied on elegantly simple mechanical systems, which demonstrated remarkable reliability, rarely succumbing to jamming even amidst the intense stresses of violent aerial maneuvering. Japanese defensive systems, conversely, placed a premium on exacting precision and formidable firepower, often integrating complex hydraulic systems. While these undoubtedly offered superior accuracy, they concurrently necessitated incessant calibration and adjustment by highly skilled armorers, a resource-intensive approach. The flight control systems within the captured flying fortress operated via a seemingly rudimentary arrangement of cables and pulleys, which appeared almost primitive when juxtaposed with the sophisticated hydraulic boost systems favored by the Japanese. Yet, American pilots consistently reported exceptional handling characteristics across a spectrum of flight conditions. The mechanical controls imparted direct, tactile feedback, enabling pilots to instinctively perceive the onset of stall conditions. In sharp contrast, hydraulic boost systems possessed the inherent drawback of potentially masking dangerous flight attitudes, sometimes to a point where recovery became an impossibility. Matsumura's profound realization was that simplicity, far from being an indicator of inferior engineering, served as compelling evidence of a more astute and superior design philosophy. The design of the fuel system articulated American priorities with an uncompromising clarity. The B-17's fuel tanks were constructed from straightforward aluminum sheets, lined with robust rubber bladders that could be replaced expediently in field conditions using only basic tools. Its self-sealing capability stemmed from specialized rubber compounds engineered to automatically close small punctures, thereby providing essential protection without recourse to intricate mechanisms that were prone to failure under the extreme duress of combat. Japanese fuel systems, conversely, employed highly sophisticated pumps and valves, which, while offering precise fuel management, inadvertently introduced multiple potential points of failure that could render an aircraft stranded far from its home base. As his dedicated team painstakingly compiled their comprehensive analysis throughout the summer of 1942, Matsumura began to grasp the monumental scale of Japan's strategic miscalculation. It became devastatingly clear that American engineers were not merely focusing on constructing individual aircraft. Rather, their ingenuity was directed towards designing expansive production systems capable of churning out thousands of aircraft, often utilizing a workforce with limited specialized training. Every single component was meticulously optimized for the trifecta of mass production, facile field maintenance, and unwavering operational reliability, a departure from an emphasis solely on peak performance or engineering elegance. The stark quantitative data underscored this narrative with unassailable clarity. B-17 production figures, for instance, had ascended to an impressive 48 aircraft per month at Boeing's Seattle facility alone, with blueprints already in place for the activation of additional production lines as military contracts continued to expand. Each B-17 bomber necessitated approximately 15,000 man-hours for its completion, a figure dwarfed by the 32,000 man-hours required for a single Shinszan prototype. This staggering disparity meant that American workers possessed the capacity to construct 3 flying fortresses in the same time frame it took Japanese craftsmen to complete just 1 heavy bomber. The comparisons concerning material usage were equally sobering in their implications. A B-17 typically consumed 2 tons of aluminum alloy, whereas the Shinszan, designed for comparable capabilities, demanded a significantly higher 1 tons. American designers had masterfully eliminated superfluous material through a rigorous, systematic analysis of stress distribution, thereby creating structures that were precisely strong enough to fulfill operational requirements without incurring any excess weight that would diminish performance. Japanese engineers, in contrast, had constructed structures that were often stronger than strictly necessary, operating under the assumption that an abundance of strength was inherently preferable to a meticulously optimized design. The profound disparities in maintenance philosophy became glaringly evident through a thorough examination of the captured bombers' logbooks, which had been remarkably recovered intact from the crash site. B-17 squadrons executed scheduled maintenance, employing standardized procedures that could be proficiently completed by any trained mechanic operating in the field. Routine engine changes, for instance, typically required a mere 6 hours using universally common tools, while repairs to the hydraulic system demanded only basic mechanical knowledge. Shinszan maintenance, however, necessitated the involvement of specialized personnel who possessed an intricate understanding of the unique characteristics of each individual aircraft, rendering squadron-level repairs utterly unfeasible under the demanding conditions of combat. Perhaps most revealing of all was the American approach to battle damage repair. B-17 structures were intentionally engineered to fail gracefully, meaning that damage would tend to concentrate at specific, predictable points that could be patched effectively using field expedients. Aluminum skin panels could be readily replaced with sections salvaged from other damaged aircraft, while structural repairs typically utilized standard aluminum angle stock, a material easily procurable from virtually any industrial supplier. Japanese aircraft, conversely, mandated custom-manufactured parts, crafted to precise specifications, a requirement that made field repairs impossible and consequently forced damaged aircraft out of service for protracted periods. By October of 1942, Matsumura had arrived at a definitive conclusion, one that was destined to fundamentally reshape Japan's entire strategic approach to bomber development. His insight was that the B-17 superiority did not stem from advanced technology or the use of exotic materials. Its true advantage lay in the fact that American engineers had successfully addressed the correct problem. Instead of striving to construct the perfect bomber in an abstract sense, they had engineered an aircraft that could be efficiently manufactured, reliably maintained, and effectively operated by ordinary individuals navigating extraordinary circumstances. The path forward for Japan was now strikingly clear, yet undeniably daunting. It necessitated the complete abandonment of the Shinszan program and a fresh start, with American design philosophy serving as the foundational blueprint. However, 18 months into the brutal Pacific War, precious time for such profound and fundamental shifts in approach was rapidly dwindling. The urgent communication originating from the Imperial Navy's Central Command reached the Nakajima facility in Kisumi on September 14, 1943. This telegram contained an array of specifications that seemed less like practical engineering directives and more like an audacious challenge. Kenichi Matsumura, a leading figure in aircraft design, absorbed the demanding requirements twice before carefully placing the document upon his drafting table, fully grasping that Admiral Yamamoto's staff had, in essence, tasked his team with defying the very principles of physics, all under the daunting constraint of an 18-month deadline. The list of demands was formidable: a maximum velocity of 370 km, a speed surpassing any extant heavy bomber globally, an operational ceiling of 33,000 feet, providing sufficient altitude to evade the majority of intercepting fighter aircraft, an extended operational radius of 4,600 miles when carrying a reduced bomb load, a range adequate for missions to the American West Coast and back, and a maximum bomb payload of 8,800 pounds, enough destructive force to cripple significant industrial infrastructures. These stipulations appeared to be the fantastical desires of individuals unburdened by the practicalities of calculating power-to-weight ratios or the complexities of aluminum allocation. However, Matsumura possessed a distinct advantage, having dedicated the preceding 18 months to an exhaustive study of captured B-17 bombers. The insights gleaned from American engineering philosophies had coalesced into a groundbreaking understanding. Japan's fundamental misstep lay in merely replicating American hardware without adopting the underlying American design methodology. The forthcoming bomber, christened the GE-8N Renzan or Mountain Range, was destined to completely discard the DC-4E design paradigm and instead fully embrace the core principles that underpin the success of American aircraft. Please stay with us and watch the end of the video. We will be grateful for your like and subscription. Please also leave a comment about where you are from and what you think about the video topic. Throughout that autumn, working sessions frequently extended well past midnight, as Matsumura's dedicated team systematically dismantled every preconceived notion that had guided Japanese aircraft development since the 1930s. Traditional Japanese engineering had long prioritized individual artisanal craftsmanship and the meticulous optimization of individual components, a philosophy that, while producing aircraft of remarkable technological sophistication, often created manufacturing nightmares. In stark contrast, American engineering emphasized systematic integration and streamlined production efficiency, resulting in aircraft that were sufficiently robust to be mass-produced in the thousands. The resulting G8N design, which emerged from these intensely focused sessions, bore no resemblance to any prior Japanese bomber. Elegant, clean lines replaced the intricate, complex curves of earlier models. A singular vertical stabilizer was adopted, eliminating the problematic twin-tail configuration that had persistently undermined the Shinszan's directional stability. Mid-mounted wings were incorporated, offering enhanced structural efficiency, while simultaneously improving accessibility for maintenance crews. Every single component was meticulously engineered with a hierarchy of priorities. Reliability came first, performance second, and ease of manufacturing third, a profound reversal of the traditional Japanese aircraft development philosophy. The selection of the appropriate power plant proved absolutely pivotal to the entire program's ultimate success. Rather than merely adapting existing engines, Matsumura successfully persuaded Navy procurement officials to allocate funding for the specific development of the Nakajima NK9KL Homar radial engine, tailored precisely for the G8N's demanding mission. Each individual engine was projected to generate an impressive 2,000 horsepower at military power settings, collectively providing a formidable 8,000 total horsepower to propel an aircraft designed to weigh 38,360 pounds when empty. This strategic decision finally allowed the power-to-weight ratio to align with American standards, while simultaneously exceeding American performance benchmarks. The Homar engines thoughtfully integrated crucial lessons derived from meticulous teardowns of Wright Cyclone engines, placing a strong emphasis on operational reliability over the pursuit of mere peak performance. The cylinder cooling fins featured simplified designs, allowing for efficient mass production, while the internal components were manufactured to tolerances that expertly balanced precision with the imperative of production speed. The supercharging systems were specifically optimized for sustained high-altitude operation, ensuring full power output even at altitudes where intercepting fighter aircraft would find it exceedingly challenging to maintain stable formations. Airframe construction represented another significant departure, abandoning the complex forgings and custom machining processes that had rendered the Shinszan prohibitively expensive to manufacture. The G8N's wing spars utilized aluminum extrusions, which could be readily produced on standard rolling mills, with reinforcement strategically concentrated at points of high stress rather than being uniformly distributed throughout the entire structure. Skin panels were ingeniously designed for straightforward replacement using common workshop tools, thereby facilitating battle damage repair even under challenging field conditions. The sophisticated electrical system design was a direct reflection of hard-won understanding regarding the practical requirements of combat maintenance. Standardized connectors and a meticulously color-coded wiring scheme eliminated any guesswork during essential repairs, while accessible routing allowed mechanics to rapidly diagnose and trace problems. Power distribution was achieved through proven American-style bus systems, a significant improvement over the intricate switching networks that had made Shinszan electrical repairs a highly specialized task, often requiring days of arduous troubleshooting. The fuel system design prioritized survivability without compromising ease of maintenance. Self-sealing tanks incorporated robust rubber bladders that could be easily replaced by squadron-level mechanics, while critical fuel pumps and valves were strategically positioned for effortless access during routine scheduled maintenance. This comprehensive system provided precise fuel management capabilities, essential for extended long-range missions, while deliberately eliminating the complex automation that had previously introduced multiple potential failure points in earlier designs. The strategic placement of defensive armament meticulously balanced formidable firepower with critical structural integrity, effectively circumventing the debilitating weight penalties that had consistently plagued previous Japanese bomber designs. Gun positions utilized standardized mounts, offering the flexibility to accommodate various weapon types, while ammunition feeds relied on robust mechanical systems engineered to function reliably even under conditions of violent maneuvering. This integrated installation provided comprehensive defensive coverage without introducing excessive drag or weight issues that would compromise the aircraft's crucial flight performance. The inaugural G-8N prototype majestically emerged from Nakajima's final assembly hangar on August 23, 1944. Its gleaming silver aluminum skin reflected the intense illumination from work lights that had burned continuously for 3 months. Matsumura himself personally oversaw the meticulous pre-flight inspection, rigorously checking every system that collectively represented 4 years of accumulated knowledge about the essential factors that determined an aircraft's success under demanding combat conditions. Test pilot Captain Teishi Shirani successfully completed his maiden flight on October 23, 1944, subsequently reporting handling characteristics that not only met but exceeded all initial expectations. A validated maximum speed of 368 mph at an altitude of 26,245 feet confirmed the accuracy of the design calculations, which had confidently predicted American-level performance from Japanese manufacturing ingenuity. Service ceiling tests conclusively affirmed the aircraft's capability to operate effectively at 33,465 feet, an altitude comfortably above the operational band where most intercepting fighter aircraft could maintain optimal combat effectiveness. Range testing proved equally impressive, with a maximum distance of 4,039 miles unequivocally demonstrated during meticulously monitored fuel consumption flights. The G-8N possessed the capability to reach targets on the American West Coast and safely return to bases situated in the Mariana Islands, thereby finally providing Japan with the strategic bombing capability that had been a central promise since the very inception of the Pearl Harbor planning. The inception of the G-8N program, a pivotal undertaking in Japan's wartime aerospace ambitions, coincided with the strategic planning that had led to events such as the attack on Pearl Harbor. However, by early 1945, as the third prototype of this formidable bomber concluded its rigorous acceptance trials at Kisumi Airfield, the broader geopolitical landscape that had originally necessitated its development had irrevocably deteriorated. The relentless onslaught of American B-29 superfortresses systematically dismantled Japan's industrial infrastructure, while carrier-borne aircraft freely patrolled the skies above the home islands, unchallenged. Consequently, the crucial aluminum resources, indispensable for the production of the G-8N, were urgently diverted to bolster defensive fighter initiatives, offering a more immediate, albeit desperate, shield against the devastating bombing campaigns that were progressively reducing Japanese urban centers to desolation. Ultimately, only a mere 4 G-8N prototypes would ever see completion before Japan's unconditional surrender brought a definitive and permanent end to the entire ambitious program. This advanced aircraft, which finally presented a viable solution to Japan's long-standing strategic bomber deficiency, unfortunately emerged far too late to exert any meaningful influence on the conflict's inevitable conclusion. It stood as a testament to engineering brilliance, a true masterpiece of design and construction. Yet it was rendered utterly irrelevant by the harsh realities of industrial capacity and logistical limitations, an arithmetic of production that no amount of technical ingenuity could surmount. Kenichi Matsumura, a central figure in its development, observed the fourth prototype as it gracefully taxied to its designated parking position on August 10, 1945. He undoubtedly harbored the somber knowledge that American technical delegations would soon arrive to meticulously scrutinize the pinnacle of Japanese engineering prowess, a creation forged when unburdened by the necessity of merely replicating foreign designs. The G-8N encapsulated the entirety of Japan's accumulated knowledge and refined methodologies in constructing aircraft with unparalleled precision, yet the arduous journey to mastering this right way had consumed too much precious time to strategically alter the war's trajectory. The solemn announcement of Japan's surrender reached the Nakajima facility at Kisumi, precisely at noon on August 15, 1945. The Emperor Hirohito's voice, imbued with historic gravity, crackled through radio speakers, conveying to the Japanese populace the stark reality of the war's cessation. Within the cavernous engineering hangar, Kenichi Matsumura stood silently beside the imposing fourth G-8N prototype, witnessing his dedicated team of 200 specialists grapple with the profound implications of this declaration. 4 arduous years of intensive research, development, and tireless effort had culminated not in victory, but in Japan's unconditional defeat. Outside, high above the very facility where this advanced bomber had been conceived, American B-29 superfortresses continued their methodical campaign of destruction against Japan's industrial heartland. Their persistent contrails starkly visible at altitudes the G-8N could theoretically achieve, but would now, tragically, never operationally contest. Please stay with us and watch the end of the video. We will be grateful for your like and subscription. Please write a comment below about where you are from and what you think about the video topic. The irony of the situation was absolute and deeply poignant. Japan had, at long last, successfully engineered a strategic bomber that could genuinely rival American performance metrics. Yet this achievement materialized precisely as American strategic bombers were completing the systematic annihilation of Japan's capacity to manufacture aircraft in any substantial quantities. The unforgiving numerical disparities that underscored the program's ultimate failure were etched into Matsumura's consciousness with an almost mathematical clarity. A mere 4 G-8N prototypes, completed against the staggering 12,631 B-17 flying fortresses churned out by American factories. This represented a stark contrast between 4 aircraft embodying the zenith of Japanese engineering innovation and an American production apparatus that delivered more bombers in a single month than Japan had managed to construct during 4 years of concentrated national effort. On September 3, 1945, American technical intelligence teams arrived at Kisumi, embarking on a mission to document and analyze Japan's advanced wartime technologies. Under the leadership of Colonel Harold Watson from the Army Air Force's Technical Intelligence Unit, Matsumura personally guided the examination of the G-8N prototypes. He meticulously elucidated design decisions and performance characteristics to the American engineers, who approached the aircraft not with triumphalist satisfaction, but with a palpable sense of professional curiosity and respect for their adversaries' ingenuity. These captured German and Japanese aircraft, which they were now diligently cataloging, consistently represented remarkable technological achievements that had, regrettably, for their creators, emerged too late to sway the ultimate outcome of the global conflict. Colonel Watson's comprehensive assessment, meticulously documented in technical reports that would remain shrouded in classification for many decades, readily acknowledged the G-8N's truly impressive capabilities. Nevertheless, his analysis concurrently underscored the insurmountable industrial limitations that had inexorably sealed the program's fate. The bomber boasted a maximum speed of 368 mph, a figure that actually surpassed the performance of early B-29 models, while its service ceiling of 33,465 feet matched the stringent standards set by American heavy bombers. Furthermore, its remarkable range capability of 4,600 miles would theoretically have enabled devastating strikes against the continental United States from forward operating bases in the Marshall Islands. However, these compelling performance specifications, while impressive, presented only a partial picture of the broader strategic reality. Watson's expert team meticulously calculated that the fabrication of a single G-8N necessitated approximately 42,000 man-hours of highly skilled labor. This figure stood in stark contrast to the mere 18,000 man-hours required for a B-29 Superfortress, thanks to its construction on Boeing's highly automated and efficient production lines. While Japanese craftsmanship undeniably yielded aircraft components that were often technically superior in their individual execution, the sheer scale and efficiency of American mass production generated aircraft that proved strategically decisive through their overwhelming numerical superiority, rather than through individual component perfection. The detailed analysis of material consumption unveiled even more pronounced disparities. Each G-8N prototype, for instance, consumed a substantial 7 tons of aluminum alloy. In comparison, American heavy bombers typically averaged a more efficient 2 tons, a result of systematic optimization in their structural design. Japan's total national aluminum production in 1944 reached its zenith at 142,000 tons. Theoretically, this quantity would have been sufficient to construct approximately 16,000 G-8N bombers, assuming no other aircraft were being manufactured simultaneously, an utterly unrealistic scenario. In stark contrast, American aluminum production in 1943 alone exceeded 920,000 tons, a colossal output that comfortably supported the simultaneous production of fighters, bombers, transport aircraft, and even civilian goods, all without encountering critical resource allocation conflicts. Matsumura, in his interactions with American interrogators, found himself compelled to articulate the fundamental philosophical divergences that had profoundly shaped Japanese aircraft development throughout the entirety of the war. Traditional Japanese engineering, he explained, placed an uncompromising emphasis on the absolute perfection of individual components. This approach resulted in aircraft that were veritable marvels of precision manufacturing, yet they simultaneously became nightmares of production complexity, demanding meticulous hand craftsmanship. Conversely, American engineering prioritized the seamless integration of adequately performing components into highly effective overall systems. This methodology facilitated the creation of aircraft that could be efficiently manufactured by a workforce with minimal specialized training, employing standardized procedures and robust assembly lines. The comparative study of engine development proved particularly enlightening for the American technical teams, as they sought to extract crucial lessons from the Pacific War experience. The NK-9 KL Hamar radial engines powering the G8N each generated a robust 2,000 horsepower, leveraging advanced supercharging systems that represented the cutting edge of Japanese technology. However, these sophisticated engines demanded complete overhauls every 120 flight hours, primarily due to inherent metallurgical limitations in their high-stress components. In stark contrast, the Wright R-3350 Cyclones installed in the B-29 produced an even greater 2,200 horsepower and were capable of operating for an impressive 400 hours between major maintenance interventions. This superior operational availability was a direct outcome of systematic reliability engineering that consciously prioritized sustained performance and operational readiness over the pursuit of fleeting peak performance metrics. Manufacturing philosophy differences permeated every facet of aircraft production, creating a stark divergence in national capabilities. For instance, the G8N's robust wing spars were meticulously machined from solid aluminum billets, a process demanding precision tooling and many hours of intricate setup time for each individual component. In stark contrast, the B-29's wing spars were ingeniously assembled from readily available aluminum extrusions and sheet metal stampings. These American components could be churned out en masse using sophisticated automated machinery, efficiently operated by a workforce of semi-skilled technicians. While the Japanese methods undeniably yielded structurally superior components, exhibiting unparalleled craftsmanship, the American approach, focused on industrial efficiency, produced components that were entirely adequate for their purpose, and crucially, in such overwhelming quantities that they effectively nullified any marginal performance advantages held by the more exquisitely engineered Japanese parts. Further operational realities, which had remained entirely invisible during the tranquil peacetime development phases, were starkly illuminated by a comprehensive maintenance requirements analysis. The intricate systems of the GE-8N, for example, necessitated specialized tools and highly trained mechanics for even routine maintenance procedures, rendering any significant squadron-level repairs utterly impossible under the chaotic and resource-constrained conditions of active combat. Conversely, the B-29 systems were meticulously engineered with practical maintenance in mind, allowing for repairs to be performed by mechanics possessing only basic training, utilizing common tools readily available at virtually any forward airfield. This fundamental difference meant that a damaged superfortress could often be returned to combat readiness within a mere matter of hours, whereas a similarly damaged G8N would languish for weeks, requiring specialized repair work at major, well-equipped maintenance facilities far from the front lines. We invite you to stay with us and watch the end of this insightful video. Your support means the world to us, so we would be immensely grateful for your like and subscription. Please also consider leaving a comment below, sharing where you are from and what your thoughts are on the crucial topic discussed in this video. By October of 1945, American technical teams had diligently concluded their exhaustive documentation of Japanese aircraft development programs, ultimately arriving at profound conclusions that were destined to profoundly influence post-war military procurement strategies for many decades to come. Their findings unequivocally demonstrated that technical excellence, no matter how brilliant or innovative, was rendered strategically meaningless without a commensurate industrial capacity to support it. The most sophisticated aircraft in the world, embodying the pinnacle of engineering achievement, simply could not compensate for fundamental, insurmountable limitations in manufacturing capability and the effective allocation of vital resources. Matsumura's concluding interview with Colonel Watson transpired on November 8, 1945, a poignant encounter that took place alongside the impressive fourth G-8N prototype. Around them, American transport crews were busily preparing to ship the magnificent aircraft to Wright Field for an exhaustive and detailed analysis. The ensuing conversation, however, deliberately steered clear of intricate technical specifications, instead focusing intently on the overarching systemic factors that had, in the end, decisively determined the war's outcome, despite Japan's undeniable achievements in individual aircraft performance. The brutal and devastating arithmetic of industrial warfare had, in a most unforgiving manner, rendered even the most exceptional engineering excellence utterly irrelevant in the grand scheme of conflict. To illustrate this disparity, it was revealed that more B-17 flying fortresses, a staggering 4,750 aircraft, had been shot down over the battlefields of Germany alone than Japan had managed to construct of all heavy bomber types combined throughout the entirety of the war. American factories possessed an astonishing capacity to replace combat losses at a rate that far outstripped Japan's ability to produce new aircraft, thereby creating a mathematical impossibility that no amount of technical sophistication or individual design brilliance could ever hope to overcome. This stark reality highlighted the decisive role of industrial might. Colonel Watson's ultimate assessment, meticulously recorded in classified reports that would subsequently shape the American understanding of industrial warfare for the impending Cold War era, underscored lessons that extended far beyond the immediate realm of aircraft development. His conclusions emphasized that ultimate victory belonged not to those nations that merely constructed the absolute best weapons, but rather to those nations capable of building entirely adequate weapons in overwhelming, almost unimaginable quantities. The G-8N Renzan, in its exquisite design and advanced capabilities, symbolized the absolute zenith of what Japanese engineering could achieve when theoretically unfettered by resource constraints. Yet, these very resource constraints, often overlooked in the pursuit of perfection, were revealed to be the fundamental and inescapable reality of modern warfare. Matsumura, with a profound sense of resignation, watched as the impressive fourth prototype slowly vanished into the cavernous cargo hold of an American transport aircraft. In that moment, he fully grasped the painful truth. His team's greatest engineering achievement, a testament to their dedication and skill, was destined to serve merely as a museum exhibit, a historical relic rather than fulfilling its intended purpose as a formidable operational weapon of war. 4 years of intense, dedicated development had culminated in the creation of an aircraft that possessed the genuine potential to have dramatically altered the war's trajectory. Had it only been manufactured in the vast quantities that Japan, tragically, was never truly capable of achieving. The crucial lesson, learned with such devastating finality and far too late, was profoundly simple in its essence.